This is the second of the modules devoted to count data analysis. We have seen that in addition to binary data, count data is one of the fundamental types of discrete data for which we need to develop a separate class of regression models. In the previous module, we have seen the log linear model, which is the standard model for Poisson variables. In this, we will do a quick recap of the log linear model, look at the underlying assumptions which lead to the Poisson distribution, and see that some of them can be quite restrictive. In particular, we will be concerned with the assumption that the mean and the variances are assumed to be equal for the Poisson distribution. Now, of course, it is not necessary that for any count series that the mean and the variance will always be equal. When this does not hold, we have a situation of what is called over-dispersion or under-dispersion. We shall see some examples of why this occurs, and although in this module we will not go into the mathematics of it, we will also see an application of the remedy for this situation, which is fitting something called quasi-likelihood estimation. Finally, we shall see that there is a connection in the situation where we have a multinomial response and the Poisson log linear model. The learning objectives for this module. We will first mention the log linear model, which is the standard model, as you know, for count data. We will look next at the underlying assumptions of the standard model and see that they can often be restrictive. We shall look in more detail at the situation of over-dispersion, and finally we will see that there is a connection between the log linear and the multinomial response model. The Poisson log linear model. As you know, this is the standard model used to model count data, and a very good reason for this is that when you have a Poisson situation, if you write out the likelihood, you will see that the canonical link for the Poisson family of distributions is the log link. As you know, in the situation where we use a canonical link, the score equations simplify, the behavior of the coefficients is better in terms of their asymptotic distribution, and for this reason, the canonical link is often the default link in many software packages. Thus, the log link is the default link if, for example, you wish to fit a Poisson regression model in R using the GLN function. So the assumptions of the Poisson log linear model, we first assume that we have data on an outcome yi, which is a count, and a p vector of covariates xi for a set of n individuals. For the ith individual, we assume then that yi conditional on xi follows a Poisson distribution with weight lambda I, where lambda I is equal to the expectation of yi given xi, and we know that since we have assumed a Poisson distribution, this is also equal to the variance of yi given xi. Thus, in terms of the variance function which we have defined for the generalized linear model, the variance function here is given by the identity function, that is variance equal to mean, and we do not have any extra parameter, which is the scale parameter, in addition to lambda. However, since we have a regression situation, our purpose is to relate yi to certain covariates xi, and we do this by using the log link, which says that log of lambda I is a linear function of the p covariates. So log of lambda I is equal to beta naught plus beta 1 x1 to beta p xp. We next want to interpret the coefficients. We have seen, for example, that when we have binary data and the logistic model, for example, the regression coefficients have very easy interpretations in terms of log odds and log odds ratio. This, for example, could be one attractive aspect of the logistic model, which makes it more popular over the probit model. So let us see if there is a similar natural interpretation of the coefficients for Poisson regression for the log linear model. Now note that the log linear model implies that lambda I is equal to e to the power beta naught plus beta 1 x1 to beta p xp. Thus, if we set all other covariates x1 to xp equal to 0, we get lambda I is equal to e to the power beta naught. Thus, exponential beta naught can be termed to be the baseline rate. Recall that lambda I is a rate. It is the rate at which a certain process occurs over time, leading to the count yi. In some situations, it is not natural for us to think of setting x1 to xp equal to 0. For example, what if x1 were age, x2 were weight, and so on. In this situation, we can standardize the coefficients by including, instead of x1, x1 minus x1 bar, where x1 bar is the mean of x1 over the observed sample, and similarly for the other covariates. In this case, e to the power beta naught turns out to be the baseline rate, where as baseline we consider an individual for whom all the other covariates are set equal to their mean. For j equal to 1 to p, we can write out this model setting xj equal to some particular value x, and then setting xj equal to x plus 1, assuming that all other coefficients, all other variables are fixed. Taking the difference of these two models, we see that e to the power beta j turns out to be the rate ratio, that is the ratio of the corresponding lambdas for a unit increase in xj, assuming all other covariates held constant. Thus, the interpretation of the coefficients in this situation is that beta naught is the baseline rate and beta j are the rate ratios for a unit increase in the corresponding covariates. Now, in the situation where we have a cohort study and a rare event, it can be shown by performing a Taylor series expansion that the beta j's can be interpreted as the corresponding relative risks. Let us look at the underlying assumptions which have led to the Poisson model. The first assumption states that within each small interval, which may be of time or of space, of length delta t, we have these two assumptions. Firstly, that the probability that one event is observed, that is exactly one event is observed, is approximately proportional to the length of the interval. That is, it is approximately equal to lambda times delta t for some rate parameter lambda. The probability that more than one event is observed within this interval is small o of delta t, and it can be shown that this leads to limit delta t tends to 0, the probability of observing more than one event divided by delta t equal to 0. These are the assumptions which lead to the Poisson probability mass function. The Poisson model thus makes two strong assumptions. Firstly, the assumption of homogeneity. The assumption of homogeneity assumes that the rate at which the event occurs, that is lambda, is constant over time. In our regression setting, we have rates lambda 1, lambda 2 to lambda n, which vary over individuals, that is, they are different for each individual depending upon their covariates, but they are constant over time. We also have a property of memorylessness. The memorylessness property states that if we consider two non-overlapping intervals, then the number of occurrences of the event in these two intervals can be considered to be independent. The assumptions for the Poisson model are thus quite restrictive. Further, when we have a regression model, and particularly in the case where we have continuous covariates, so that we do not have more than one individual with the same set of covariates, checking the assumptions is tricky. So what are the assumptions for the Poisson regression model? Firstly, that the log expected counts are linearly related to the covariates, the outcomes are independent, and the variances are equal to their mean. In the case where we have factors as covariates, it might be possible to bin the data and plot the mean counts over categories to see if the assumption of linearity can be assumed to hold, or whether we should expect some other link. An alternative would be to fit the model using different links and to compare the value of the log likelihood to get the best model. The assumption of independent outcomes can be violated when, for example, we are looking at clustered data. So, for example, we might be looking at, say, a certain blood count, but rather than taking random observations from the entire population, we first select a number of families and then look at a subset of individuals within each family. In this case, as members of the same family share the same genetic makeup, it might not be reasonable to assume that the data are independent. One way around this is to use something called a mixed model, and we shall look at the details of this in a forthcoming module. The third assumption is that the variances are equal to the mean, and this is the assumption which we shall explore in more detail in this module. So, over-dispersion. Over-dispersion arises for count data, or indeed it can also arise for other data, when the variance exceeds the mean. Now note that we can also have a situation of under-dispersion, where the variance is less than the mean, and we shall see later that both of these can be modeled in the same way. For now, let us try to identify situations where we can expect to see over-dispersion. The first is where we are modeling a random number of counts. So let us assume that Z1, Z2 to Z capital N are all counts, and we are looking at their sum y equal to Z1 plus Z2 plus Zn. Now we know that if capital N is fixed, in this situation the distribution of y will also be Poisson, and so it does not lead to any additional complications. However, let us consider the situation where capital N itself is random, that is, the number of individuals whom we are looking at is a random variable. In this situation, we know that expectation y is given by expectation of y is equal to expectation of capital N into expectation of capital Z. This can be shown easily by conditioning on capital N and showing that for capital N equal to some fixed value, say small n, expectation of y is equal to small n into expectation of z, and then using the fact that expectation of y can be written as expectation of the conditional y, expectation of y given n. Similarly, using properties relating the variance of y to its conditional mean and variance, that is, variance of y is equal to expectation of capital N into variance of z plus variance of n into expectation of z square, we can show that the variance of y is equal to expectation of n into expectation of z square. So if we compare the mean and the variance, we see that if expectation of z square is greater than expectation of z, then we would expect to have a situation of overdispersion. A second situation where overdispersion could arise is when we are modeling inter-subject variability. So let us assume that we are looking at some outcome y which is distributed as Poisson with the rate parameter equal to z. But z, instead of being constant over the population, itself has a distribution which we shall assume is given by the gamma distribution. In this case, again, by using the properties of conditional expectation or by writing down the likelihood explicitly, we first note that expectation of z is equal to some value which we assume mu, and variance of z is mu by phi. Now there are some alternative formulations of the gamma distribution, and if we assume this formulation, that probability of y equal to y given two parameters mu and phi is of the form as given in this slide, it is possible to rewrite the mean and the variance as expectation y equal to mu and variance of y equal to mu into 1 plus phi by phi, where we see that the multiplication factor exceeds 1, and hence we again have a situation of overdispersion. Overdispersion can also occur in many other ways. The two situations where we have looked at overdispersion in the last two slides, we have seen that it is possible to model the mechanism by which overdispersion arises. So in the first case, overdispersion arises because we are looking at a random number of counts, and in the second case, overdispersion arises because the rate parameter is not constant but itself has a gamma distribution across the population. In these situations, because we can write down the mechanism, we can also write down a parametric model for it, and hence use any parametric means of inference such as likelihood-based inference. However, there are two other situations which may result in overdispersion. The first is misspecification of the model, and the second is omission of covariates. Now, as contrasted to the case where the mechanism is known, in many situations we might not know what the relevant covariates for inclusion are, and thus it is necessary for us to conduct diagnostic checks after fitting a model to examine whether overdispersion is present or not. Now, as we do not know any readily available parametric model which allows us to write down a general formulation for the mean and the variance where the two are not necessarily related, we can no longer use likelihood-based inference. In a subsequent module, we should look at the procedure which is indeed used in these situations, which is something called quasi-likelihood. Now note that in many observational studies, it is quite natural to assume that all relevant covariates have not been measured, or indeed that it is not possible to measure all relevant covariates. Thus, overdispersion is almost always a concern in any observational study. A reassuring concept is that the difference in parameter estimates is often to the order of capital OP phi to the power minus 2, where phi is a scale parameter which we shall define explicitly when we consider formal models for overdispersion. And thus, for practical purposes, very often the difference in the regression coefficients may not be significant. However, it is good to assume that the mean and variance are not necessarily identical, and when we look at quasi-likelihood estimation, we will see that it is possible to get a data-based estimate of the scale parameter without making any restrictive assumptions. Without going into the mathematics of quasi-likelihood, let us look at a situation where it is applicable for an observational data set. Now, this is the wave damage data which has been studied in detail by McCulloch and Nelder, and it looks at the number of reported damage incidents and aggregate month service by ship type, year of construction, and period of observation. The data courtesy is J. Crilly and Hemingway from the Lloyd's Register of Shipping, and as I mentioned, the data set has been studied in more detail by McCulloch and Nelder. An appropriate model for this data is the log linear model, which relates the expected number of damage incidents to aggregate month service, the effect due to ship type, the effect due to year of construction, and the effect due to service period. Now, McCulloch and Nelder postulate that there is some inter-ship variability in the accident proneness of a ship. That is, two ships with the identical set of covariates do not necessarily have the same accident proneness. For this reason, they postulate that instead of using variance of y equal to expectation of y, let us assume that variance of y is some constant sigma square into expectation of y, and let us get a data-based estimate of sigma square. So that is the model that they have fitted in this book, and the table here gives the corresponding estimates and standard errors. Now note that they have not done this using the likelihood, but by using something called quasi-likelihood. So here are their findings from this study. Main effects are significant. The estimated coefficient of the offset term, which is the length of service, is 1. Interactions with both service period, ship type, year of construction are all insignificant. There is an outlier which we can identify by formal regression diagnostics. And finally, that there is evidence of inter-ship variability. And the reason for this last statement is that the scale parameter estimated from the data turns out to be 1.69. Thus, the variance, instead of being equal to mean, is equal to a factor 1.69 times the mean. In a later module, we shall look at the exact mathematical model which led to these estimates. So here is another way to present the data, which looks at the predicted number of damage incidents by ship type and year of construction. Finally, let us look at the connection between log linear and multiple response models. Now let us suppose that y1 to yk are independent Poisson variables with means mu1 to μk, and that we wish to test the composite null hypothesis h0 mu1 equal to mu2 equal to μk equal to some constant which we parameterize as e to the power beta naught. The alternative hypothesis is that for some unknown parameter beta 1, the log linear model holds, which is log mu j equal to beta naught plus beta 1 xj. Xj, of course, are some given constants. Now, the natural test statistic turns out to be t equal to summation xj yj, and this is conditional on m equal to summation of yj, which we know to be the sufficient statistic for beta naught. The conditioning is necessary because to perform inferences about beta 1, we need to eliminate this nuisance parameter beta naught. Now, unconditional moments of t are as given on this slide. Expectation of t is approximately of the form summation xj y naught by k, and variance of t is approximately summation xj square y naught by k. The conditional moments of t are as given on the last two lines of this slide, and we can see, for example, that the estimate of the unconditional variance of t is quite different from the exact conditional variance. Note that t can be regarded as the total of the random sample of size n with replacement from the finite population x1 to xk. Under h0, the k values are selected with equal probability. Under h0, the probabilities are exponentially weighted in favor of the larger x's if beta 1 is 0 and vice versa. The Poisson log likelihood function for beta naught beta 1 in this problem is given by Ly beta naught beta 1 equal to beta naught summation yj plus beta 1 summation xj yj minus summation exponential beta naught plus beta 1 xj. If we make a parameter transformation tau equal to summation exponential beta naught plus beta 1 xj, the log likelihood for tau beta 1 is as given on the third line of this slide, and this can be written as the sum of two terms. The first term is the Poisson log likelihood for tau based on m. The second component is the multinomial log likelihood for beta based on the conditional distribution of y1 to yk given y0 equal to m, which follows multinomial with parameters m and pi. Pi j being equal to e to the power beta 1 xj by summation exponential beta 1 xk. The important point here is that the marginal likelihood based on y0 depends only on tau, whereas the conditional likelihood given y0 depends only on beta. Now, if there is no information available concerning the value of beta naught and hence of tau, we must conclude that all of the information about beta 1 is given by the conditional likelihood given y0. In this module, we have looked at some alternative models for count data analysis. The standard model, as you know, is the log linear model, but there are some situations in which the standard log linear model does not give a good fit. In this module, we have revisited the concept of the mean and the variance being equal and seeing how violations of this assumption can occur. We have touched upon something called quasi-likelihood estimation through an example. And finally, we have also seen that there is a connection between the Poisson log linear model and the case of multinomial responses. In a future module, we will look at more details of the quasi-likelihood estimation procedure, which is used in situations where we have count data where the mean and the variance are not necessarily equal.